Aloha and welcome. In this video, we're going to be talking about everyone's favorite subject, blockchain. If you've been listening to anybody that wants to talk about Bitcoin or Ethereum or any other type, you've most likely heard of blockchain. Most likely the people that have been making pitches to you to buy these things have probably known nothing about the actual technology that goes behind it, but we're going to go ahead and delve into some of that at a higher level right now. So let's take a look at it. So blockchain. Blockchain is a type of digital ledger, and it's an electronic system or database that's used to record and track transactions. So these ledgers, they're utilized in finance, business, and record-keeping applications to monitor and audit transactions. So an example of this is banks are going to be using digital ledgers to record and manage customer transactions. Well, blockchain does the same thing, except it's decentralized. We're not relying on a central authority there like a bank or something like that. So it's decentralized and distributes a digital ledger. It takes that digital ledger that records and links the transactions and it spreads it across a network of computers. So one of the first ones out there, if not the, was the Bitcoin cryptocurrency, and that uses blockchain to record and verify transactions. So blockchain, so blockchain enables the creation and maintenance of open public ledgers. So the concept of an open public ledger is a transparent record-keeping system that is accessible to the public, everybody can see it, and enables anyone out there to verify recorded transactions. So an example of this would be the Ethereum blockchain is an open public ledger for smart or self-executing contracts. So blockchain can be used to secure any type of information. You can use this for buying and selling of property. You can use it for just about anything. Unfortunately, you'll see that a lot of criminal organizations also like to use this, and you'll hear a lot if you listen to a lot of hacking stories. And we've talked about this already, malware attacks where you have, let's say, ransomware. Ransomware never asks you to send a check to a location. They always ask for Bitcoin. So that's one of the reasons it's easier for criminal activity to be conducted using these types of currencies. So anyway, we've got in the book a table that goes through everything. It talks about the architecture, security, trust, and application for both the traditional digital ledger and the blockchain. So the differences between traditional and blockchain, for architecture, you've got a centralized traditional ledger, so it's all in one place. Whereas blockchain, you're spreading that across a network of computers and trusted individuals. So you've got, well, trusted individuals, not really so much, but known individuals. So security, for traditional ledger, you've got centralized security measures such as data encryption and access control. The other side, blockchain, you're going to be using cryptographic services to enable transparency and tamper-resistant record keeping. On the trust side of it, for traditional digital ledger, you've got a central authority such as a company or government, whereas in blockchain, it's going to be, again, relying on cryptographic verification and decentralized consensus across a network of computers. For application, how to use traditional digital ledger? Well, on that side, it's going to be the general transaction recording. For blockchain, you're going to be using it in cryptocurrencies, smart contracts, and decentralized finance, also known as DeFi. We have at the heart of this, the thing that enables doing some of these verifications is the concept of a Merkle tree. So Merkle tree spelled M-E-R-K-L-E tree. Merkle tree is a hierarchical data structure used for verifying the integrity of large data sets. So a Merkle tree facilitates secure data verification in diverse applications. So if we look at a Merkle tree, it's organized into a binary tree format. Binary trees have a lot of properties. We won't really need to get into the properties that make it important, but just know that it's a tree structure. So you've got a head node at the top, and then you've got tree branches, and then the end ones are what we call leaves. So the end nodes that have no branches off of it are called leaves. So with the Merkle tree, the data elements are going to be initially stored in the tree's leaves, in other words, the very end of the thing, with each of the nodes containing a data elements hash. So a Merkle tree is built by repeatedly hashing the child nodes. Child node is, so you've got the parent here, and then whatever comes down from it in the tree structure is going to be considered it's going to be considered a child node. So the Merkle tree is built by repeatedly hashing the child nodes to create parent nodes until a single top node is existing, and that top node is going to be the Merkle root, or what we call the root hash. So it's the topmost hash in the Merkle tree, and it uniquely represents the entire data set's cryptographic hashes. So Merkle path is a sequence of nodes that connect a data element to the root. So data element's Merkle path consists of the hashes of the sibling nodes along the path from data element all the way up to the top. And I'll show you an example of that now. So I'm going to go ahead and share the book right here. So we're looking here at a Merkle tree. And if we were to run this, it would explain it. So we're going to start. We've got these leaves. These are the end nodes, essentially. So we've got data A, data B, data C, data D. H of D and H of C, all this means is it's the hash of D and hash of C, hash of B, and hash of A. We've got the data A, so we've got this. So when we click on next, you're going to see that the hash of child nodes are paired together to create parent hash nodes. So we've got A and B here, and that goes to create a hash of A and B. Over here, we've got hash of C and D, which goes to make C and D here. And then the iteration continues until you get to that single hash, which is H of A, B, C, D, right there. And then, so the Merkle path of data D, so the one down here, it's going to be for DC, it's going to be for DC, but also A and B over here. So you're going to have H of A, B, C, D. So that's your Merkle path. Um, so for the blockchain block structure, you've got a header and you've got a body. So the header is the block component that provides the metadata about the block and includes the block hash, the previous block hash, blockchain protocol version, the block creation timestamp, and Merkle root of the block's transactions. And the block body is the block component that contains the content or the payload of the block. That's going to have your tree structure in it, and which, depending on the blockchain's intended purposes, can consist of transactions or application-specific data. So every new block here is cryptographically linked to the preceding block because we're hashing it with the previous hashes here. So when we do that, we're chaining them all together. So as it says here, every new block is cryptographically linked to the preceding one through the previous block hash, forming a chain that is tamper resistant and difficult to alter retroactively without altering all subsequent blocks. So once a block is added to the chain, the block becomes immutable. Immutable, you're going to hear about this here, but it's also a term from programming. It means essentially unchangeable. So you cannot change it. And that's what's going to ensure the integrity of the block's transaction. So you can't erase these things. So the Merkle root optimizes data transmissions and verifications within a blockchain network. Nodes can validate the inclusion of a particular transaction in a block by computing the hashes along the transaction's Merkle path, removing the need to download and verify the entire thing. So that's all you need. And then here, there's a good example of it. You can go ahead and click through to see the example, but it's a block is composed of the block header and the block body. The block body includes the metadata about the block, and the block body contains the transactions. So it shows you here the different transactions. So blocks transactions are organized in a Merkle tree structure in the body block, or the block body, and the Merkle root is computed. So this is the Merkle root right there, and that's going to be put up here in the block header. So you see it gets the Merkle root. It's going to have the timestamp, the version, and then the hash of the previous block is added to the block header, and the hash of the entire block is computed and stored. So you're going to take the whole hash and store that as well. Then every new block is going to be cryptographically linked to the preceding one, so you can see the links between the preceding one, the next one. So you're going to be cryptographically linking the two by hashing them to form a chain. And that brings us to the consensus algorithms. So Since this thing is decentralized, we've got to figure out, how to verify the validity of the transactions and reach consensus before we can add a new block in here. So that's why we have the consensus algorithms. It enables a network of decentralized nodes to agree on the state of a shared digital ledger at any time. So consensus algorithms, those are going to be critical for achieving a common and distributed understanding of the blockchain's transaction history. So you've got three main ones. You've got proof of work, you've got proof of authority, you got proof of stake, and they each operate in totally different ways. So proof of work is going to, it's a blockchain consensus algorithm that requires all the network, or like requires several of the network participants to perform computationally intensive tasks known as mining. So they're typically looking for value that when you combine it with the block's data, it's going to produce a certain hash. So this is extremely computing intensive. And not only is it computing intensive, but it's also electricity intensive. And they found that Bitcoin, which uses this, is one of the most expensive algorithms out there. And if you're thinking about, hey, I'd like to use my computer on a network to do this kind of work, you really need to sit down and think your way through it and say, okay, how much energy am I going to be using? How much does that energy cost me? And therefore, how much am I actually making if I get this little fraction of a Bitcoin piece to do this transaction? So you really have to sit down and think about that. Again, there's also ethical and environmental issues to take into account because they say that with Bitcoin, the amount of energy usage just to do the transactions rivals the electric usage of certain nations out there. So that's pretty impressive. So Bitcoin, which uses this, it's not very environmentally friendly. Then we've got proof of authority. Proof of authority is used by Celo, a blockchain platform for financial services. And it works totally different. So instead of having all the network participants do really intensive math, they're going to basically choose validators, and they're going to choose them based on their identity and reputation. So this seems a little bit less, independent than the previous one, where everybody's working on it, but you're relying on people who's on their identity and their reputations. So that's something to think about. So the authority to create the new blocks is only going to be granted to known and trusted participants. So it's not fully democratized in that sense. And the last one you've got is proof of stake. And proof of stake is a totally different type. That's going to be uh, based on it's going to be selecting network participants to create the new block that's based on the amount of assets that the participant holds and is willing to stake. So staking is the act of committing as an asset as collateral to participate in the consensus process. So you're putting up your own, for example, here it's Ethereum, but you're putting up Ethereum, to do these calculations, and if something goes awry, you could be on the hook for that. So this proof of staking, it's yeah, it does have the drawback that if something goes wrong, you're financially reliable for it for doing that work. So that could be a little bit dangerous. But the nice thing about this one is it is a lot more energy efficient than other methods. So we've got a chart here that goes through the differences here. So we've got the POW, POA, and POS from above. So for consensus algorithms, the proof of work, that one's where you've got the participants doing math problems. The proof of authority, that's going to be validators chose based on the authority, their reputation. Then the POS, the proof of stake, that's where the validators are going to be chosen based on the amount of stake that they've got, how much they're willing to put up to validate. Then energy efficient, as I said, the proof of work, that's the highest level of energy consumption, which rivals, several countries. You've got the proof of authority, and that one has lower energy consumption compared to the previous one, but still not as low as the proof of stake, which is the most energy efficient. Then you've got the security to consider. So the proof of work is going to be really high security due to the computational effort that's involved there. Your proof of authority is going to be moderate security, but because it relies on trusted nodes. Then the other one, the proof of stake, is going to be security that's guaranteed through economic incentives. So for incentives here, Proof of work, your participants are motivated by block rewards and transaction fees. So they actually get Bitcoin for doing this mining, for doing all this stuff, for the wear and tear on their computer and all the money that, the electricity costs it has. It will, they'll get paid back a small, tiny, tiny, tiny fraction of Bitcoin for every transaction that they do. So you'd really have to sit that down, put it into an Excel spreadsheet to see if you're making any money at all by doing this. Then for proof of authority, validators are motivated by maintaining the network authority. So it's really the reputation they're wanting to uphold. So that's their stake in it. They're like, hey, I want to be seen as, a network authority here. So that's why they're doing it. And then for the proof of stake, they're going to be motivated by staking rewards. So yeah, so that's the three different incentive structures there, but know the differences between them. Just remember, particularly that the proof of work is going to be the most intensive, and it goes on a scale. It's proof of work, then proof of authority, and then proof of stake. Just know what they're based on, what the incentives are for those. And the last thing we talked about before, Bitcoin's environmental impact. As it says, Bitcoin's total electricity consumption has been higher than Australia, Greece, and Switzerland. Granted, those aren't extremely large countries, but it is considerable how much Bitcoin is using in terms of energy to do that. So anyhow, that's our high-level introduction to blockchain. This is a general understanding of how it works. Remember, it's built on this idea of a digital ledger. It's open and it's public. Anybody can see it. It's decentralized. Uh, you can watch it, participate in the process. It's based on this idea of the Merkle tree and the Merkle tree properties that, the hashing is what allows you to go and check and see if, you can tell if a transaction's in there just by looking at the hash on the Merkle root. So, yeah, so the structure, we've got the block header and the block body. The block body is where you have the actual the tree. The block header is where you have a lot of metadata in there, like the Merkle root, the timestamp version, the previous hash. And remember that we've got these cryptographically chained together through the hashes of them. So that is what makes it, that's what adds the integrity. And then we've got the three different types. We've got proof of work, proof of authority, and proof of stake for determining the blockchain consensus algorithms there. So if you have any questions about this, let me know. I'd be happy to help you. But that was your introduction to blockchain. So I will see you in the next video. Aloha.